and then they get a random forest. This is a random forest classifier, like they said. All right, so okay, I'm not going to delve deep. I'm going to give So I'm going to provide this tutorial, and you can go with it step by step to see what actual process that you go through from the process of just importing the data and to the process to the end of evaluating the score of your model. Okay, so bear with me. I'm just trying to look for the part that has modeling right here. Okay. So this part here is very important, this process here. You break the combined data set into a trained set and a test set. Use the test set to build a predictive model. Evaluate the model using the test set, and then test the model using the test set and generate the output for submission. All right. Okay, so I have not gone through the code really deeply, but yeah, I've just given you a high level of like what you do, and I'm also going to provide more resources to help guide you through the process. So the final step of what I'm going to talk about is how to actually, after getting this model, training it, testing it, we've seen that it is a supervised learning, it can be a regressor, it can be a classifier. How do you actually evaluate it? Okay, how do you evaluate the results of your model? And then this will be our last piece. All right, so you finally built your machine learning model to predict future prices of Bitcoin. So in this case, the use case is predicting the future prices of Bitcoin, so that you can finally become a multi-billionaire. All right, but how do you know that the model created was any good? It is very important to access evaluate the performance of your model. So in this article, I'm going to talk about several ways you can evaluate your machine learning model, and it even has the code provided. So there are two parts to the article. How do you evaluate regression models? How do you evaluate classification models? Like we had seen those categorizations before. And also, there is also more information about regression and classification there. So more specifically, I'm going to cover the following matrices. So these metrics, you're going to be seeing them very, all right. So you're going to be seeing these terms very commonly, so it is very important to know what they mean. So more specifically, I'm going to cover the following metrics. So these are metrics that help you see the performance of your model. The R squared, the adjusted R squared, the mean absolute error, the mean squared error. How do you, when you see a confusion matrix and all the related matrices, how do you interpret that? The F1 score, and then area under the curve, ROC curve. How do you interpret that? So also I'm not going to go very, I'm just really mostly introducing these terms and telling you what they really mean, and then, yeah, I really advise that you delve deeper and see how much more you can learn about them. Okay, so for the first metrics that we're going to see in order to evaluate a model, we're going to start with evaluating regression models. For example, like a linear regression, we're going to use R squared, and we're going to say that R squared is a measurement that tells you to what extent the proportion of the variance in the dependent variables is explained by the variance in the independent variables. Okay, that's a loaded statement. In simpler terms, while the coefficients estimate the trends, the R squared represents the scatter around the line of best fit. We're going to see an example here, right here. So you see the coefficients that we're talking about, especially like on your regressor, like the y is equal to mx plus c, m will be a coefficient. Those coefficients will estimate the trend, like the slope, how is the line fit, but the the scatter around the line is represented by what they call the R squared. So for example, if the R squared is 0.8, then 80% of the variation can be explained by the model inputs. So that's how you interpret the R squared. If the R squared is 1.0, that means 100%. That means that all the movements of the dependent variable are entirely explained by the movements of the independent variable. To show a visual example, despite having the same line of best fit, so we can see this line of best fit is the same. It's the exact same formula of these lines. But the R squared on the right, which is this one, is much higher than that one on the left. So you see, so what the R squared simply illustrates is the scatter of the data points around the line of best fit, the line of best fit. So we can see the R squared right here is much higher than the R squared right here. Okay, so this is the equation for how they come up with the R squared. This is 1 minus explained variance divided by the total variance. I'm not going to delve deep into this explanation, but yeah. So to get it, also there's a library in sklearn called Matrix, where you can get the line of best fit by passing it the y true and the y predicted. So the y true is the outcome variable. That is the dependent variable. So the one that has been, this is in this case, this would be the test data set. So what you know is true and what the model has predicted. How does it perform? What is the R squared? So that is what the R squared means. So we go on to the adjusted R squared. So every additional independent variable added to the model always increases the R squared. Therefore, a model with several independent variables may seem to be a better fit even if it isn't. This is where the adjusted R squared comes in. The adjusted R squared compensates for each additional independent variable and only increases if each variable improves the model above what is possible by probability. There's a couple of ways to find the adjusted R squared in Python. Yeah, so this is another measure of model performance, and they're just trying to tell you that the more independent variables or the more features you have, you'll get an increased value of R squared. But that does not necessarily mean that the model is fitting the data very well. So the adjusted R squared comes in to compensate for those additional independent variables and trying to see with every additional independent variable, how much better does it improve the model, okay? So this is the manual calculation. We're not going to go through it. And then this is the option. This is when you use a library that is already there to get the adjusted R squared. Then we go on to the mean absolute error. And remember, all these are still under the regressor evaluation techniques, okay? So when you see these terminologies, just know like where they fit in the whole picture. So the absolute error is the difference between the predicted values and the actual values. Of course, you would always want to get the absolute error. Like your model is going to always have a margin of error. It is going to predict something and then it probably isn't right. So you always want to see, okay, how much error do I have? So these are the true actual, I know the true labels, and these are the predicted values. So the absolute value, the absolute error is the difference between those two. So that's the mean absolute error is the average of the absolute error. So you just get the absolute error by subtracting the values of the predicted values minus the values from the true values, and then to get the mean is just basically the average. So this is the calculation for it, and then that is where you can get it from, the libraries, okay? So then now so this is the mean absolute error. Then there is also mean square error. Mean square error is similar to mean absolute error, except that you take the average of the squared differences between the predicted values and the actual values. So this is where you just, instead of just taking the absolute difference, you take the squared differences between the two, okay? Because the differences are squared, larger errors are weighted more highly. And so this should be used over mean absolute error if you want to minimize large errors, okay? So because of the squaring factor, because of the squaring part, so the large errors are going to be magnified in weight, and then, so that's why you would choose the mean absolute error of your model. Okay, so we have seen 3 examples of evaluating regression models. So that is the R squared, the adjusted R squared, and the mean absolute error actually 4, and then mean squared error. And then the examples for classification models, like the models that we just saw in the Kegel Titanic dataset. For example, how would you how would you evaluate the different models? So the first one is going to be a confusion matrix. So you get a confusion matrix and you see the related matrices. So a confusion matrix is also known as an error matrix. It's a performance measurement for assessing classification models. So below is an example of a 2-class confusion matrix. So a confusion matrix, what it tells you is how many true negatives, false positives, and true positives are there. So if the actual value is no, how many of them were predicted to be no? So that means it's a true negative. So if the actual value is no, how many of them were mispredicted to be yes? And that is a false positive. So if an actual value is yes, how many values of them were falsely predicted to be no? And that's a false negative. And if an actual value is yes, and how many of them were actually predicted truly to be true, to be yes, so that's a true positive. Okay? So within the confusion matrix, there are some terms that you may need to know, which can be used to calculate various matrices. So a true positive, this is the outcome of the model correctly predicts the positive class. So like I just said, so when the outcome of the model, it's an actual yes, and then the model also predicts a yes. So a true negative, it's an actual no, and the model also predicts an actual no. Okay? So that is what we want here. We want true negatives, we want more true negatives, and we want more true positives. So a false positive, that is type 1 error, is when the model incorrectly predicts the positive class. So it is supposed to be a no, but it says it's a yes. Okay? So a false negative, that's a type 2 error. The model incorrectly predicts the negative class. So it's supposed to be a yes, but it gives it a no. So these are the ones we don't want. We want to minimize the false positive and the false negatives. So how you get the accuracy? Now that you know these terms here, the number of the matrices that you can calculate from these terms. So accuracy will be equal to the fraction of the predictions that the model got right. So the number of correct predictions divided by the total number of predictions. This is really straightforward. And then the recall attempts to answer the question, what portion of actual negatives was identified correctly? Okay, so you're going to see what is accuracy. You see accuracy, the fraction of the correct predictions over the total number of predictions. And yet the recall will be the proportion of the actual positives that was identified correctly. So this will be the true positives over everything else that is positive. So true positive over true positive over the true positive plus the false negative. Then there's precision. It attempts to answer the question, what proportion of the positive identifications was accurately correct? Okay, to really hit the point home, the diagram below is a great way to remember the difference between precision and recall. It certainly helped me try. Okay, all right. So this diagram, it certainly helped him remember what the difference between recall and precision is. I'll just give it. I'll give it up to you to just try and interpret it. But The whole point is trying to see what is true positive, what is true negative, and what is recall. Introducing these terms to you: recall, precision, accuracy, as a way of evaluating models. Okay, so this is code for the confusion matrix. You can see this matrix library already gives you direct ways to access these: confusion matrix, accuracy, recall score, precision score. So I definitely advise that you read up on these to understand further like what each implies in terms of your accuracy of your model. So the last one, I believe, no, the second last one, that is the F1 score, and under the classification, evaluating classification models. So the F1 score is a measure of a test's accuracy. It is the harmonic mean of the precision and the recall, and it has a maximum score of 1, the perfect precision and recall, and a minimum of 0. So overall, it's a measure of the preciseness and the robustness of your model. There are 3 ways to calculate the F1 score in Python. All right, so this is the first method, that's the second method, that's the third method. Okay, so you want to use the F1 score if you're interested in measuring the preciseness and the robustness of your model. And it is between a range of 0 and 1. So 1 will be the perfect precision and recall, and then the opposite will be 0. So the last measure of evaluation measure of classification models will be the area under the curve. You will see this very often, area under the curve and the ROC curve. The area under curve is a performance measurement for classification problems that tells us how much a model is capable of distinguishing between classes. Okay, the higher area under the curve means that the model is more accurate. If you want to learn about it, Sarang did a great job of explaining it. Please do follow these links, because I have just done a high-level explanation, and more details will be in these links. So to calculate the area under the curve, you can replicate the code. So this is just calculating the area under the curve. And that's it. Now you know how to evaluate your machine learning models and determine if they're actually useful. We'll go over various ways to improve your machine learning model. So yeah, so that's about it. So just a recap of what I have just taught from start to finish. We introduced a bit of machine learning models. What is machine learning? Under machine learning, there's supervised learning and unsupervised learning. And then within supervised learning, which we've been focusing on, there's categories, regression and classification. And then under regression, we've seen there are models like linear regression, which we touched a bit about. But then I advise that you go and look up all the other models: logistic regression, ridge regression, lasso regression. Okay, then under, so that was the regression bit. Then under classification, we looked at, logistic regression is supposed to be a classifier. So it's only linear regression that is under regression, and the other ones are ridge and lasso. So under classification, we saw logistic regression, we saw SVM, support vector machines. We looked at naive Bayes, we looked at, what are the other ones we looked at? Okay, yeah, you can always go back and see which ones they are. Yeah, they're right here. K-nearest neighbors under the classification bit. Then from there we went to see, okay, how would we, like an example of a classification example of how can you, given a data set, how can you tell if someone survived on the Titanic based on their class, based on their age, based on their, is it class, age, and I think, what was it? Based on their class, age, and the embarked class. So we looked at how the data was pre-processed, and we also looked at the point at which they got the performance of the different models. But there I wanted to emphasize that I did not really show a good representation of how the process you go through for training, the process you go by first dividing your data into a training set and then a test set, then training your model on the test training set, and then testing it using the test set so that you can evaluate the performance, and then also evaluate different models according to their performance. And then that is where we ended up by saying how do we evaluate the models. So we've been looking at the R-squared, these different matrices for evaluation, R-squared, adjusted R-squared, mean absolute error, what do they mean, area under the curve, confusion matrices, what do they mean and how do they fall into this whole large picture. And then, yeah, so that is where I'm going to stop. And then Grace will take on to unsupervised learning. And then I'm also going to share these resources, and then you can go and just delve deeper. And I hope that was a very good guide for a start. Thank you.